So, welcome to this lecture. Let us just recall what we had done in the previous lecture. In the previous lecture, we had started looking at various types of functions. We looked at linear functions, we looked at quadratic functions, and then we looked at how to define or what motivates one to define what are called exponential functions. So, we gave a rough outline of how exponential function can be defined. Hope you have revised that. Let me just summarize what is exponential function, what are its properties, so that we are able to go ahead. So, exponential function is defined for every positive real number a, of course, not equal to 1, and this function is a function from the real numbers taking values non-negative values, and it is denoted as f of x is equal to a x. It is something like a raised to power x with the following properties. 1. The domain of this function is all real numbers. So, it is defined for all real numbers. The range is a set of all positive real numbers. So, that means for every positive real number there exists a real number such that x such that a raised to power x is equal to that real number y. So, range means for every positive real number y there exists a real number x such that a raised to power x is equal to y. So, the domain is the set of all real numbers and the range is the set of all positive real numbers. It behaves very much like the ordinary powers, the laws of exponents work, namely for this function a raised to power x plus y. So, what is this? This is the image of f of x plus y. So, a raised to power x plus y is same as a raised to power x into a raised to power y. That means, if you take two real numbers x and y and take the image of x plus y, then the image of x plus y is equal to the product of the images of x and y respectively. And similarly, if you take a real number x, take its image, that will be a raised to power x, that will be again a real number, you can take its image again under the function f. So, this will give you a raised to power x raised to power y, and we claim that this function has the property that this is same as a raised to power, these powers multiply essentially x into y. And for every a bigger than 1, so this number a is bigger than 0. So, and we have assumed it is not equal to 1. So, it is either bigger than 1 or less than 1. If it is bigger than 1, then it is a increasing function, and for less than 1, it is a decreasing function. So, increasing means as you go from left to right, the graph will be going upwards, and decreasing means as you go from left to right, the graph will be bending downwards, it will be dropping down. For every positive real number a greater than 1, not equal to 1, of course, f of 0 is equal to 1. That means what? That means there is, for this 1 is a positive real number, for this image, pre-image is nothing but 0. So, 0 is mapped into 1 for, so that means a raised to power 0 is equal to 1 for every a. And it keeps, so for a bigger than 1, we said it is an increasing function, and now it says that limit of x going to infinity f x equal to plus infinity. That means what? That means as you keep on increasing f, okay, going as f as x keeps on increasing, it goes to infinity, and there is a typo where it should be minus infinity. So, limit x going to minus infinity is equal to 0. So, as you keep on going to the left, the function approaches the value 0, and on the right the function goes on increasing as large as you want. So, here is it should be minus infinity. For a between 0 and 1, the other way around happens, namely limit x going to infinity of f of x is 0 if a is less than 1, and it is limit of x going to, this is minus infinity again, is equal to plus infinity if x goes to infinity minus infinity. for a less than 1. So, the behavior of a bigger than 1 and a less than 1 is almost opposite of each other. Okay. And so, it quite clear that the graph of a raised to power x and 1 over a raised to power x are reflections of each other. So, if one tries to plot them, this is what it look like. For the number bigger than 1, this is a blue line when a is here a is less than 1. So, that is why it is written as 1 over a. So, for a real number bigger than 1, its power is this blue, and it is less than 1 non negative, of course, then it is this. So, they are reflections, and 0, the both values for both is equal to 1. How this graph is, I have plotted this graph using a software, but why does the graph look like this for the exponential function? Of course, we have said that as you go from left to right, it is increasing, and it goes on increasing, and it keeps on decreasing as you go to the left side. Then why it should look like a nicely rounded kind of graph? That requires more properties of functions, calculus properties. We will see it later on that this is actually the graph of both of them. So, this is just to illustrate why graphs are important and what is the relation between the function a raised to power x and 1 over a raised to power x, geometrically how they look like. The function, both these functions, or for any a bigger than 0, this function x going to a raised to power x is called the exponential function, and this number a is called the base of that function. So, it is the exponential function with base a. When this base is a number e is a very special number in the real line which is bigger than 1. It is a number between 2 and 3, and its proximate value is 2.178. It is a irrational number. So, you cannot write exact value of this. In the previous lecture, we had seen how to define e using limits of sequences. This is called an Euler number. So, when this particular base e is taken, then we say that the exponential function has natural base. So, when we say we are considering exponential function with natural base, that means the value of a is taken as e, which is the Euler number. So, for example, this is we saw in the previous lecture also, in terms of this function, the continuous compounded interest with rate of interest r% in time t is given by. So, p t is the principal that it will grow into in time t, p 0 is the initial investment or the principal amount, r is the rate of interest, and t is the time. So, e raised to power r t, the exponential function appears in representing, if you want to represent continuous compounded interest at the rate r for time t. Let us look at some observations, that for a bigger than 1, we said that a raised to power x is an increasing function. So, values increase. So, normally for a bigger than 1, the exponential function a raised to power x is called the growth curve, and for a less than 1, because it is decreasing, it is called the decay curve. And the functions f x equal to a raised to power x and x to just look at the exponential function a raised to power x and the function x to the power a. A is fixed in both of them. So, here is the base being raised to power which is varying. Here the power is fixed and the base you can think it is varying. Okay. So, what is the difference between these two functions, a raised to power x and x raised to power a? Both are very similar functions, as we have seen a raised to power x is increasing function, x to the power a also is an increasing function. Okay. But there is a difference between the two, namely the a raised to power x grows much faster than x to the power a. Just to give you an illustration, let us look at a equal to 2 and x is equal to this number. Okay. So, here is values of 2 to the power x and here is a power x square. So, 2 to the power 10, if you compute it is 1024 and 10 to the power 2 is just 100. So, you can already see the difference appearing for the value x is equal to 10. When we take x to be 100, then 2 to the power 100 we can compute it is 12,676, whereas for 100 to the power 2 it is just 10,000. So, all more difference appears. When 2 to the power 1000 you can compute, it is the value is this, and we have not written the other values. You can see that this value is much bigger than this value. Okay. So, this says that the exponential function grows much faster than the power function. One can prove that this growth is faster using higher order calculus, so we will not be doing that. Okay. The exponential function with base e, the Euler number has special significance. It is useful in modeling problems involving growth or decay. We have already seen for the compound interest, the exponential function appears, that is a growth function. For example, let us look at the population of a tribe, say it was 750 in 1947. So, here is an example how this exponential function is used. And population is growing at certain rate. So, let us say this is the equation which gives the population at time t is 750 into e raised to power 0.05 t. It is very much similar to the compounded interest, where the rate of interest you can think of as this. So, the growth condition, the growth curve, whenever you want to model, it is e raised to power some constant times t. As time t varies, that will give you the growth. Okay. When t is equal to 0, this value is 1, that gives you the population, the principal amount or the starting point. So, for in this example, if you want to know when you start observing what is the population, so that is t equal to 0, so that is 750 here. So, that is what is also given. As time passes, the population is growing, and we are saying that this model for the growth is given by this equation. So, the basic thing is exponential raised to power a t or alpha t or c t, some constant times t, where that constant is positive. So, that is a growth model. So, this will keep on increasing as time t increases. So, this is unlimited growth. It will grow as much as if you do not put any checks, it will grow very much. It can grow as large as you want it as time grows. So, you can also use it for modeling total revenue of a firm. For example, let us look at an example. Suppose it is expected that the revenue of a firm increases at the rate of 10% annually. Okay. So, the revenue of a company or a firm is increasing at 10% annually, and the initial, that is say when you start observing, the total revenue is T 0. So, then what is the growth model? So, total revenue will be T 0. Okay. So, e raised power 10% is 10 by 100 into t. So, that is the growth model for the revenue of a company. It is growing at the rate of 10%. So, in case you want to say there is a decline, so how does that how is that represented by exponential function? The only difference comes is it is e raised power minus that rate at which it is decreasing times t. So, if there is instead of growth increase, there is a decrease in the revenue, then the model will be total revenue is T 0 e raised power minus 0.1 t, and if it is growth, it is e raised power plus 0.1 times t. So, that is the difference. The negative sign makes it either increase or decrease. So, in this earlier model, the revenue will keep on increasing, right, and in this model the revenue will keep on decreasing. One can also have a in between thing, whether the revenue or the growth is not as large as you want it, but it gets limited to something. So, let us look at example of that. So, let us say the population of certain bacteria is governed by this function. So, p of t is 10 times 1 minus e raised to power minus 0.2 t. So, in this scenario, what is when t is equal to 0, this value is 1, okay. E raised to power 0 is okay. When so that is 1, so that is 0. So, let us say that is 0, okay. Right. So, now what is happening? So, let us observe that as t increases, what is happening to 2.2 t, that is going to increase, okay, but there is a negative sign. So, e raised power that is going to decrease. So, this is going to decrease. This quantity as t increases, this quantity is going to decrease, because the e raised to power something, that is same as 1 over e raised to power 0.2 t. So, 1 over 2 e is exponential of 0.2 t. As t increases, the denominator will increase. So, 1 over that will decrease. So, this is going to decrease, and what it is going to decrease to? Essentially, you can feel heuristically that this power becomes 0. So, this is going to become to 10. So, one says as t goes to infinity, as t increases, right, e raised power minus 2.2 t goes to 0, and hence p of t, the population stabilizes or eventually will reach to 10 as t goes to infinity, right. So, here the population is okay. There is a limited growth, okay. Right. So, it stabilizes eventually to 10, okay. Right. So, now let us just point out here, see, as t goes to infinity, we have taken this value as sort of it goes to 0, it is coming closer and closer to 0. So, this is a concept of a limit that we shall study soon. So, this is at present it is only intuitively, heuristically, that as t goes to infinity, right. So, as t goes to infinity, this term, the power is going to go to minus infinity. That means, this is going to 1 over infinity, that is eventually sort of going to become smaller and smaller, that is going to become 0. So, this is going to become 10. So, this is an intuitive way of saying that the exponential function also can be used for limited growth or limited decay. So, population here we are saying it will stabilize to 10, right. So, these are the applications of exponential function. It can be used for unlimited growth, unlimited decay, or limited growth or limited decay. So, this is a model for the limited. Let us look at one very particular special function which will not be dealing much hopefully in this course, because that requires the concept of functions of two variables. Look at this function. The output of any product, right, depends upon many inputs, right. When something is being produced, it depends on many things: land, capital, labor, raw material, and so on. So, let us say for the time being, for our consideration, the output, the production depends upon two things only, k and l, where k is the capital, that is the amount invested, right, and l is the labor that is being employed. So, we want to analyze the production of a certain product vis-a-vis two variables, namely k as the capital and l as the labor. So, this is a how much money you invest and how much is the labor you employ, that two are independent, they are not related to each other. So, one says k and l are independent variables, and q is a function of two variables k and l. As a particular special example of this relation q k l, is when this q k l is equal to a into capital K, right, raised to power alpha, and the labor L raised to power some beta. So, here are the two exponential functions coming into picture, where a, alpha and beta are fixed constants. So, this is a model which is known as Cobb-Douglas model for production of a certain quantity which depends on two variables, namely capital and the labor. So, here this is a product of two exponential functions, right. So, now suppose the inputs k and L, the k is the capital, L is the labor, both are changed by the same proportion, right. We want to know what will be the effect. So, they are changed by the same proportion, say lambda, right. So, that what does that mean? So, we change the capital by a scalar alpha, that is a constant of proportionality is lambda, and for L also is changed by the same constant of proportionality, that is lambda. So, we want to know how does the q change. So, let us observe. So, the new q 1, right, will be q 1 k 1 L 1, right. If the new changed k is changing to k 1, L is changing to L 2. So, if there is q 1 it is this, then what will be k 2? K 2 we know that it is proportionately changing. So, k 2 is lambda k 1 and L 2 is lambda L 2 L 1. So, proportionately k 2 by k 1 is lambda and L 2 by L 1 is lambda. So, from some value k 1 L 1, it is changed, the capital is changed to k 2 L 2, and the proportionality with the same amount of same proportional amount, same proportionality you change. So, what does that mean? So, when you are changed by the same proportion, that is reflected in this mathematics, that is k 2 is lambda times k 1 and L 2 is lambda times L 1. So, with this, what is q 2? This was q 1. So, q 2 is, you want to change it to q 2 L 2, right. So, that is q times lambda k 1 lambda L 1, because k 2 is lambda of k 1. So, that means you put the values here, okay, it is a times lambda k 1 to the power alpha lambda L 1, because what is q? Q is a k raised to power alpha. So, we want as k 2. So, this is k 2, that is lambda k 1 to the power alpha lambda of L 1 to the power beta. So, when you simplify, lambda of alpha, lambda of beta both come out as, and by the law of exponents you get lambda to the power alpha plus beta, k 1 to the power alpha and L 1 to the power beta. So, that is lambda, if you write it outside. So, lambda times alpha plus beta, inside is a L 1, a k 1 alpha and L 1 beta, that is your q 1. So, q 2 is equal to lambda times alpha plus beta q 1. So, what does how do you interpret this result? So, this says if k 1 and if k and L are changed proportionately, right, thus we have the following: if alpha plus beta is equal to 1, right, then q 1 is equal to q 2, right. In this Cobb-Douglas model, if it was k times alpha L times beta, if alpha plus beta is equal to 1, and you change proportionality proportionally q and if you change proportionality k and L, and if that alpha plus beta relation is 1, then q 1 is equal to q 2. That means, there will not be any change in the production if that condition is met. However, so this means both capital and the labor are changed by a proportion lambda, then output q also changes by the same proportion, right. So, same. Okay. Now, let us come back to the exponential function. The exponential function which is defined for a bigger than 1, a not equal to 1, was a function with which was a 1 1 function from the domain was the real line and the range was the whole of r plus. So, because it is a 1 1 on 2 function, it has a inverse function, and that inverse function is denoted by logarithmic function, log function with the base a. If this is a, then it is called the log function, a logarithmic function with base a. So, this is a function, is the inverse of the exponential function. Exponential function was from r to r plus. So, the inverse function is from r plus to r, and it is defined by the property that log of a, right. This is denoted by log to the base a of x is y, if and only if a raised to power y is equal to x. So, that is a definition. One can write down the properties of this log function. Essentially, what we are doing is we are reflecting x against y. So, to do that, so note that the domain is a set of all positive real numbers, and the range is a set of all real numbers. For a bigger than 1, it is a strictly increasing function. For a less than 1, it is a strictly decreasing function, right. For exponential of 0 was equal to 1, so log of 1 is equal to 0. We had exponential of x plus y is equal to exponential of x into exponential of y, and so log function has the property the log of x y x. So, this is not comma, this should be log of the product x y is log x log y. And similarly, if you repeat it, log x to the power n is n times log x, and it goes to if a is bigger than 1, then as x goes to infinity, this goes to infinity. So, it is an increasing function which goes to infinity as x goes to infinity, and for minus 1 it goes to minus infinity. Or as x goes to 0, log of 0 goes to for a bigger than 1 to plus 1, and less than 1 it goes to minus infinity. So, these are basically properties of the log function which can be deduced easily from the properties of the exponential function. In higher calculus, one looks at the properties of the inverse function vis-a-vis of the given function, and its graph is what this looks like. So, this is a graph of the function. When the base is a natural base, that means a is equal to the Euler number, then this is the graph of the function we have written. Basically, it is the same for all functions. It is a increasing function, it keeps on increasing, goes to infinity as x goes to infinity, and it goes to 0, it goes to minus infinity as x goes to 0. So, it is basically if you draw a line y equal to x and deflect, that is a graph of e raised to power x. So, it is a reflection against the line y equal to x. So, just a few remarks that for the base a equal to e, it is called the log with the natural base, otherwise it is called the log for the common logarithm. When a is equal to 10, it is called the log function or the common logarithmic function. This is the formula which allows you to change from base a to the natural log. So, log x to the base a is log x to the natural base divided by log of that base to the power natural log. So, these are some relations between the exponential function and the log. A raised to power x is same as exponential of ln of a to the power x, and that is same as e raised to power ln of a, and that is equal to this. So, because they are inverse of each other, so that is. So, one can express x and a raised to power x in terms of natural log using these formulas. Normally, the values of in computation problems, the values of log x, ln x, exponential x are used either from the log tables or from the calculators. So, let me stop here for today's lecture by saying that we have looked at what is exponential function, we have looked at its properties today, and we have seen how it is used in various modeling of economic and commerce problems. It can be used as for a growth model with e raised power c t or alpha t. Alpha positive gives you the growth model, when alpha is negative it gives you the decay model, and then you can also change it a bit 1 minus e raised power minus alpha t, to saying that it stabilizes somewhere, right, some value. So, this is our applications of the exponential function, and not only in economics, commerce and management, it appears in many modeling problems in applied mathematics also. Thank you.